Hello and welcome back to another video. Today we're going to be going through some pretty more advanced annuity questions. We're going to have a few proofs, and then there's also going to be some questions that are just not proofs, but we have to find like present values and that kind of stuff. So let's start with question one. So question one looks like it's some proofs, and it says we have to prove these identities. So we have to prove 1 over the discount p3 is equal to 1 over the interest p3 plus 1 over p. Okay. So for these kind of questions, I often like to start writing out what we know. So we know that 1 plus the effective interest rate is going to be 1 plus the interest rate compounded p3 over the number of times it's compounded to the power of p. Okay, and then it's similar with the discount rate, except it's minus. So 1 minus d is equal to 1 minus dp over p to the power of p. Okay, so now we somehow need to, because we want to link this and this, so we somehow need to find a way to link these two identities. And the way we can link it is that we know that the discount rate is equal to 1 minus v, and v is equal to 1 minus 1 plus I to the negative 1. Cool. So now, instead of d, we can sub in this into this equation. So we can write 1 minus d, but instead of d, we're going to write 1 minus 1 plus I to the negative 1 equals 1 minus dp over p to the power of p. Okay, when you put in the negative, you're going to get 1 minus 1, so that's going to cancel out, and then this is going to become positive. So you get 1 plus I to the power of negative 1 is going to be 1 minus dp over p to the power of p. Cool stuff. So now what I'm going to do is I'm going to raise both sides to the power of negative 1 to get rid of this. So then we get 1 plus I is equal to 1 minus dp over p to the power of negative p. Cool. That's pretty good. And now, this is our big link. We have 1 plus I here, 1 plus I here. So now instead of writing this, we can replace it with this. And now we have dp, I compounded p3 and d compounded p3 in the same equation. So that's really good. So now we have 1 plus I p over p to the p is equal to 1 minus dp over p power of negative p. Great stuff. Okay. That's really good. Okay, so now I'm going to take the pth, so I'm going to raise both sides to the power of 1 over p to get rid of the p. So now we get 1 plus ip over p equals 1 minus dp over p to the power of negative 1. Cool. And instead of writing negative 1, we can write 1 over. So I'm going to write this as 1 plus ip over p equals 1 over 1 minus dp over p. Cool. Now what I'm going to do is I'm going to multiply both sides by this to get it to the other side. So basically we're going to get 1 plus ip over p multiplied by 1 minus dp over p, and when you multiply, it's obviously going to cancel out to the bottom, so it just becomes 1, so equals 1. Cool. So now let's multiply this bracket, so we get 1. If we multiply inside, we get ip over p. We multiply the outside, we get minus dp over p, and we multiply the last ones, we get minus ip times dp over p squared equals 1. Okay, this looks good. So now if we minus 1 from both sides, we can cancel it out. So cancel that, cancel that. And now what I'm going to do is I'm also going to multiply everything by p squared. So multiply both sides by p squared, because I don't want all these like fractions. So we're going to get p times ip minus p times dp minus ip times dp equals 0. Cool. That's looking good. Okay, so now, what would be a good next step? Okay, so what I'm going to do is I'm going to factor out a dp and move all of that to the other side. So we're basically going to get dp multiplied by p plus ip So basically all I've done here is I've factored out this, and then this is in the brackets, but obviously I've moved it to the side because now I'm going to say it's equal to p times ip. Okay, that looks pretty good. And now I'm going to divide both sides by this to get dp on its own, because if you have a look at the identity, I see that its dp is kind of on its own, so I kind of want to isolate it in this equation. So then we'll get dp is equal to p times ip over p plus ip. Okay. And if we go back to what we're trying to prove, we want 1 over dp. So I'm just going to do 1 over both sides. So I'm going to flip both sides. So 1 over dp is equal to p plus ip over p times ip. This is really good. And now, since this top is split, we can split it up quite easily. We can write this as 1 over dp is equal to p over p times ip plus ip over p times ip. Okay, and we see that and that cancel, and that cancel. So we get 1 over dp is equal to 1 over I p plus 1 over p. And that looks exactly like the identity we're trying to prove. So that's how you do the first one, I. Let me just label this one. Question 1A, I. Cool, that's the first one. Now let's have a look at the second one, I. Okay, so in the second one, we're trying to prove that if you don't know what the symbol means, when you have like a number and then a line, it means a deferred annuity. So basically we have an annuity for n periods deferred by m years. And we're trying to show that that's equal to an annuity for m plus n periods minus an annuity for n periods. Okay, so I think a good place to start would be to write what a deferred annuity is. So m dash, like that. So it's basically a deferred annuity which is deferred for m periods. So it's a normal annuity, but it only starts after m, like let's say years, for example. So what we can do is, if like we wanted to find the present value, we just multiply it by v, because we'd have to move it back m years. So I think this would be a good starting point. So deferred annuity is just normal annuity, but you have to discount a little bit more because it doesn't start immediately. Okay, and we're trying to show that it's equal to that. So now let's write out what this and this is. So a to the m plus n is going to be 1 minus v to the n plus n over I. And what else did we want to minus a m? Okay. So a m is going to be, just move this down, give ourselves some space. It's going to be 1 minus v to the m over I. Okay. And now we're trying to show basically this minus this is equal to that. So let's maybe do this minus this. So we can say like, therefore m plus n minus am is equal to 1 minus v to the n plus n over I minus 1 minus v to the m over I. Okay, cool. So now let's combine it, because we see it has the same denominator, so we can combine it pretty easily. So that's going to be 1 minus v to the n plus n minus 1 minus v to the m all over I. Cool. So now when you multiply this in, it's going to become minus 1, then that'll cancel. So, and this will become positive. So basically this will all just simplify to v to the m minus v to the m plus n over I. Cool. Okay, so this is pretty good. So now we kind of want to prove that they're both the same. So now we've showed this. Now let's see what this would become. So m, we said it was a normal annuity multiplied by v to the m, and that would be 1 minus v to the n over I times v to the m, which becomes v to the m minus v to the n plus m over I. And we can see that that and that are the same. So therefore it's proved. We've basically shown that that is equal to that. So if they're the same, then basically those are equal. Okay, good stuff. So that's the second one. So now let's have a look at the third one. Third one says basically have an annuity for n years, compounded p times per period, divided by, so this is like a present value. Yeah, you're trying to present value it, and this is a future value annuity for n periods, again, pthly, and you're trying to prove that it's equal to v to the n. Okay, so let's write up what each of these are. So number 3, so a to the n p is going to be 1 minus v to the n over ip. So the only difference is when it has this little p, it's just if I has to be compounded p times. Okay, and then s n compounded p times. It's very similar, except you just swap it. So it's 1 plus I to the n minus 1 over ip. Okay, cool. So now we know what these are. So now let's divide them. So ANP divided by SNP is going to be, when we divide it, when A can tip in times, I'm just going to like flip 1 over and times it. So it's going to be 1 minus v to the n over IP multiplied by IP over 1 plus I to the n minus 1. Cool, and we can immediately see that that and that cancels. So this leaves us with 1 minus v to the n over, and 1 plus I to the n, you can write this as v to the negative n, just to make it a little bit simpler. So because basically v is defined as 1 plus I to the negative 1. So if we write it like this, then this basically simplifies to like 1 plus I to the negative 1 to the negative n. So you can see that it's equal to that. Okay, minus 1. Cool. And now we're trying to prove that it's equal to, what are we trying to prove that's equal to? So v to the n. Yes, yes, yes. Okay, good. So now I'm going to factor out a v to the n from the top. Okay, so v to the n times, and I'll times it by everything. Let's put it in the middle. So if we divide 1 by v to the n, it's going to give us v to the negative n minus, and if we divide this by v to the n, we get 1 over v to the negative n minus 1. And we can see that that's exactly the same, so it just becomes 1. So this whole thing simplifies to v to the n, and that's exactly what we wanted to show. And that is all the proofs. Okay, now let's have a look at B. B says, contributions of 100 Rand per month were made to a savings account on the first day of each month from January 1995 to March 1998 inclusive, together with a lump sum of 2,000 Rand on the 1st of January 1997. Find the accumulated value of the payments on the 1st of December 1998, assuming an effective compound rate of interest of 7% per annum. Okay, so when we're given dates, it can be tricky, but it's much easier when you draw a timeline. So for B, I'm going to draw a timeline. And I think a good place to start is labeling the 0. And now let's work out the total number of payments. Total number of payments. Okay, so it says that it's paid from January 1995 to March 1998. So 95 is the first year, 96 is the second year, 97 is the third year, and 98 is the fourth year, but we only have January, February, March. We only have 3 payments at that point. So in 1995, we have 12 payments. In 1996, we have 12 payments, because remember it goes from January to December. 1997, we have 12. But then in 1998, we only have 3 payments, because it says it only goes up to March. So in total, we have 12 plus 12 plus 12 plus 3, which is 36 plus 3, which is 39. Okay. So we know that the payments go up to 39, and we're paying 100 Rand at the beginning of each year. So basically 100 at time 1, we're paying 100. Time 2, we're paying 100, blah, blah, blah. Okay. And then also says something about a lump sum. Let's read that. So it says, together with a lump sum of 2,000 Rand on the 1st of January 1997. So let's think about what point that would be. So the whole of 1995, So that's 12, plus the whole of 1996, which is another 12. So it's at time 24, because it's after 2 years. Then at time 24, we're going to have this lump sum of 2,000. We're also going to have our 100. Okay, but that's just like different to everything else. And then blah, blah, blah. Let me just put in a few. 37, 38. We have our hundreds here. And remember, it said it's paid in advance. So it says on the first day of each month. So that means that the last payment will be at time 38, because at time 39 we won't have a payment because it's always paid in advance. Okay. And they want to find the accumulated value on December 1st, 1998. Okay. So the whole of 95, that's 12. Whole of 96, that's 12. Whole of 97, that's 12. Whole of 98 except the last month, so basically 11 months. So it's basically 12 times 3, which is 36, plus 11 is 47. Okay. So I'm just trying to look for the time we're trying to accumulate to. We're trying to accumulate to time 47. So basically trying to move all of these payments to time 47. Okay. So, and it also says it's monthly. Okay. Yeah, 100 Rand per month. Yeah, okay. So we're given our interest rate as yearly. So we're given the interest rate of 7% per annum per year. Okay. So we need to convert that to a monthly interest rate. So what are we doing? We're finding the monthly interest rate. So the way you do that is you'd say basically 1 plus I is equal to 1 plus I 12, because we want the effective monthly interest rate to the power of 12. Okay, so we would say that I 12 over 12 is going to be equal to, so I'll take both sides to the power of 1 over 12 and then also minus 1, and our interest rate was 7, so it's 1 plus 7% to the power of 1 over 12 minus 1. Okay, and that's going to simplify to 0.0057, which I'll store in my calculator as A, future. Okay, so now we want to find the accumulated value. And so we're basically trying to find the future value. So we're going to want to move all of these forward to time 39. So we're going to do an annuity for that many periods. And then from here, we're going to want to move forward another 8 months to time 47. Okay, so it's going to be the monthly payment, which is 100, times S in advance, because remember we're paying at the beginning of each month. Beginning, okay. And it's for 39 periods, because this is like the first one, the second one, the third one, all the way up until time 39, beginning of the period. So for 39 periods at an interest rate of A, which we just worked out. And then we want to multiply that by, we want to move that forward another 8 months. So then we're going to multiply that by 1 plus A to the power of 8. Okay, so that deals with all our 100 payments. That gets, the annuity gets all of these to time 39, and then that times by 1 plus A to the power of 8 gets you forward to time 47. Okay, so now we just need to think about this lump sum. So it's at time 24, and we might want to move it to time 47. So it's quite clear that's 23 months. So basically we need to add 2,000 multiplied by 1 plus your A to the power of 23. Perfect. So if we expand this, it's going to be 100 times 1 plus A to the power of 39 minus 1 over 1 minus 1 plus A to the negative 1, because that's, you have to divide by this because it's in advance, multiplied by 1 plus A to the power of 8, plus 2,000 multiplied by 1 plus A to the power of 23. Cool. And if you sub this all into your calculator, you should get 6,853.08. Okay, I hope this helps. This question is quite tricky with the dates, but if you can draw your number line, it becomes quite easy. Okay, now let's have a look at question 2. So question 2 has some more identities. So this is the first one we have to prove. So to prove this one, I'm going to start with just using this. So I'm going to say AXY 1 over y. So the way we can expand this is we can write this as 1 minus v to the power of xy over I 1 over y. Okay. And I want to link this to an annuity just for xy without this. So if it didn't have this like this in brackets 1 over y, it would just look like that, right? So let's kind of like artificially make that. So let's say we just had 1 minus v over I, right? So to do that, we'd have to multiply by I for it to cancel. And then we'd still need this, so we'd need to have divided by like that, okay? So it's exactly the same, because if we cancel that, it would look exactly like that. But I've just kind of manufactured so that we can get this, because I know we're going to eventually end up with that. So we can write this as I over I 1 over y multiplied by a compounded, a for xy periods. Okay, cool. I hope that all made sense. Just a little bit of manipulation there. So what we're actually given is 1 over y times that, right? So also therefore 1 over y times a for xy periods compounded 1 over y. We're just basically going to multiply this bottom by y. So it's going to be I over I 1 over y times an annuity for xy periods. Okay. Okay, so now let's think about this. So I to the 1 over y times y, we can rewrite this in a certain way, and I think that'll make it clear how we're going to use it. Okay, so this is basically the same, because if you multiply the top and the bottom by y, that'll cancel and that'll give you the same. So basically, you can do this just to manipulate a little bit. And now I want to point to something. So imagine we're using our formula to convert between effective and nominal, right? So this will be like a side note, so I'll do it like in green. So imagine you're doing like 1 plus I is 1 plus I compounded 1 over y times over 1 over y to the power of 1 over y. If we solve for this, we're going to get I 1 over y, 1 over y. So obviously we're going to raise both sides to the power of y. So we're going to get 1 plus I to the power of y, but then we're going to also want to move this across, then we get minus 1. Okay, so I'm going to use this property. So we are basically just show that this is equal to that. So this whole thing is going to be equal to 1 plus I to the power of y minus 1. Cool. So let's see why that's useful. So I'm just going to rewrite everything we proved. So I've basically proved that 1 over y times this annuity, 1 over y, is equal to, so I'll keep that, over, and I showed that this bottom part is equal to this. So I'm going to sub that in. So 1 plus I to the power of y minus 1. And then I'm just going to multiply it by an annuity for xy periods. And now let's have a look what this looks like. This looks exactly like a future value annuity, but flipped, right? Because imagine you just had this at the top, it would be 1 plus I to the y minus 1 over I. So this looks exactly like 1 over s for y periods, right? Times a for a present value annuity for xy periods. And that's exactly what we're trying to prove. We're trying to prove that it's equal to present value annuity for xy periods divided by a future value annuity for y periods. And it's proved. Let's just double check. So we're trying to prove that that is equal to that, and we have proved it. Good stuff. Okay. So that was A. Now let's have a look at B. So B says that we're trying to show that a future value annuity for t periods plus a present value annuity for n minus t periods, all multiplied by 1 plus I to the power of n minus t, is equal to a future value annuity for n periods. Okay, so I think the best thing to do would just be to expand these and then multiply in and then see what happens. Okay, so we have, let's just rewrite what we had. So we had S for t periods plus A for n minus t periods, all multiplied by 1 plus I to the power of n minus t. Okay. So now let's expand each. So the first one expands to 1 plus I to the power of t minus 1 over I plus 1 minus 1 plus I to the power of negative n minus t. It's important that you put the brackets here. The power of I, all multiplied by 1 plus I to the power of n minus t. Okay, we can combine these because they're both over I. And when you combine them, this is a minus 1, this is a plus 1, so they'll cancel. So we'll basically get 1 plus I to the power of t minus 1 plus I to the power of negative n minus t over I. And this is all being multiplied by 1 plus I to the power of n minus t. Okay, cool. Now we can easily just multiply this into both of the things. So if we multiply this by this, the exponents are going to add. So we're going to get t plus n minus t. The t's are going to cancel. And we're going to get 1 plus I to the n. And, okay, so minus. And when you multiply this by this, again, the exponents are going to cancel. So you get negative n plus n, that cancels. And then t minus t, that also cancels. So that's all just going to become 1, because it'll basically be 1 plus I to the power of 0, which becomes 1. And that's all over I. And we can see that this is the formula for future value annuity for n periods. And we have just proved what we wanted to prove. And that's the end of question 2. Now let's have a look at question 3. Question 3 says, let X denote the present value of an annuity consisting of payments of 2,000 Rand payable at the end of each of the next 8 years, valued using an interest rate of 8% per annum, convertible quarterly. And let Y denote the present value of an annuity consisting of payments of 4,000 Rand, payable at the end of each 4th year for the next 16 years, valued using an interest rate of 8% per annum, convertible half-yearly. Calculate the ratio of X versus Y. Okay, so what we'll do is we'll first separately work out X and Y, and then we will find the ratio. So let's first do X, so 4X. Okay, so X is payable each year for 8 years, but the interest rate they give us is convertible quarterly. So we're going to want to convert that interest rate to a interest rate which is per annum. So the way we're going to do it is we're going to use 1 plus I is equal to 1 plus convertible every 4 years convertible quarterly divided by 4 to the power of 4. Okay, so then I is going to be 1 plus, and they said that the interest rate is 8%, over 4 to the power of 4 minus 1, which gives us 0.082, which I will store in my calculator as A for future. Okay, so now to work out X, because X is the present value, we have to present value these 2,000 payments. So X is going to be, so we're making 2,000 payments each time, and it's at the end of each year for 8 years. So it's going to be times by an annuity, a present value annuity, for 8 years at an interest rate of A. Cool. So now if we write the formula, so it's going to be 2,000 times 1 minus 1 plus A to the power of negative 8 over A. And when we type that into our calculator, we should get 11,387.95, which we'll store as X. And a good little check just to see if we're in the right ballpark is we have 8 payments of 2,000. So if we say 8 times 2,000 gives us 16,000. And when we present value, it's obviously going to go down a little bit. So it seems like we're in the right kind of area with 11,000. Cool. So now let's have a look for Y. So for Y, okay. So let's look how often we're making payments for Y. So it says we're paying 4,000 at the end of every 4th year. Fourth year, okay. So we're going to want to get the effective interest rate for every 4th year. So what I'm going to do is I'm going to say 1 plus I to the 1 over 4 over 1 over 4 to the power of 1 over 4 is going to be equal to, and we're given the interest rate every half year, is going to be equal to 1 plus I to the 2 over 2 to the power of 2. Okay, so now we want to solve for like just this part. So we're going to get I to the 1 over 4 over 1 over 4 is going to be, so it's going to be 1 plus I2, which was 8%, over 2, power of 2, and then we need to raise all of this to the power of 4, because we want to like get rid of that, and then we need minus 1, okay? And this is going to give us 0.3686, and I'll store this in my calculator as B. Cool. So now to work out Y, it's going to be 4,000, because remember we're making payments of 4,000 at the end of each fourth year for the next 16 years. So if we're making payments every fourth year for 16 years, then we're making 4 payments overall. So we'll times this by an annuity for 4 payments, so four lots of 4 years, at an interest rate of B. Okay, so to work this out, this will be 4,000 times 1 minus 1 plus B, power of negative 4, divided by B, and this becomes 7759.11, and we'll save that in our calculator as Y. Okay, now we just need to read the question to just make sure we get the right thing. So we need to calculate the ratio of X to Y, okay? So now our stored value in our calculator is X, divided by our stored value in calculator as Y, will give us 1.4677, and that's going to be your answer for question 3. Okay, now let's have a look at question 4. Question 4 says, an annuity is payable in arrear for 15 years. The annuity is payable half yearly for the first 5 years, quarterly for the next 5 years, and monthly for the final 5 years. The annual amount of the annuity is doubled after each 5-year period, on the basis of an interest rate of 8% per annum convertible quarterly for the first 4 years, 8% convertible half yearly for the next 8 years, and 8% effective for the final 3 years. The present value of the annuity is 2,049. And we have to find the initial amount of the annuity. Ooh, okay. A lot of information here. What do we do when we have a lot of information? We draw a timeline. So let's draw a timeline. So we know that it starts at time 0 and goes to time 15. Good stuff. Okay. So now it seems like it's broken up into 5-year segments. So I'm going to break that up. So at time 5 and then time 10. Cool. So it says the annuity is payable half yearly for the first 5 years. Okay. So from here to here, it's payable half yearly. Okay. Cool. And then it says for the first 5 years, quarterly for the next 5 years. So from this point to this point, it's quarterly. And then for the next 5 years, monthly. Okay, so then from time 10 to time 15, it's payable monthly. Okay, good stuff. And now we get to some interest rates. So on the basis of an interest rate of 8%, convertible quarterly for the first 4 years. So let's mark that 4. And from here to here, we have that interest rate convertible quarterly is 8%. And then it says for the next 8 years, for the next 8 years, it's 8% as well. That'll be from time 4 to time 12, which will be around here. Yeah, so from time 4 to time 12, it says the interest rate convertible half yearly. So I'll write a little 2 for half yearly, is also 8%. And then finally, for the last 3 years, it says the interest rate, which is the effective interest rate. So I'll just write an I, is also 8%. Okay, that's all good. And then, okay, cool. So that's all good. And then it says the annual amount of the annuity is doubled after each 5-year period. Okay, doubled after each 5 year. So let's say initially it's X, then for the first 5 years. So for like this period, it's X. Then for the next period, it's going to be double. So then here, it's going to be 2X. And then here, it's going to be double that, which is 4X. That's going to be your like monthly payments. And then it says find the initial amount. So basically, they want us to find x. So we're going to have to write a whole equation to find the present value, equate it to that, and then solve for x. So to find the present value of these annuities, we're going to have to get these interest rates into the same like time interval that the annuity is paid. So for example, like this one's half yearly, so we want an interest rate that's half yearly. This one's quarterly, so we want an interest rate that's quarterly, and this is monthly, so we need to convert this to a monthly interest rate. Okay. But the thing is, the interest rates don't match up perfectly, so I'm gonna have to do a few different cases. Okay. So let's do time 1 to time 4. Okay. So from time 1 to time 4, we want the interest rate to be half yearly. So basically, we want 1 plus, we're going to solve for I2 over 2 equals 1 plus I4 over 4 to the power of 4. Okay, so now let's sub in what we know. And then we can also solve for it. So we're trying to solve for I2 over 2. And that's going to be 1 plus 8% over 4 to the power of 4. And then to get rid of the squared, we're going to put it to the power of a half. And then we're going to have to minus this one. Okay. And when I sub that into my calculator, I get 4.04%. Okay, that's good. So now we have half yearly interest rate from time 1 to time 4, and that matches this. So now we want a half yearly rate from time 4 to time 5. So T4 time 5. Okay. So basically, that's good. We already have the nominal interest rate convertible half yearly. So all we have to do is divide that by 2 to get the effective interest rate per half year. So I2 over 2 is equal to 8% over 2, which is 4%. Cool. So we got all the correct interest rates in half yearly for this period. Now we want to get, in this period, we want to get all our interest rates to quarterly. So from time 5 to time 10, we have a half yearly interest rate. So I'm going to say 1 plus I4 over, wait, what do we want it in? We want it in quarterly, yeah. I4 over 4 to the power of 4 equals 1 plus I2 over 2 to the power of 2. Let's sub in what we know and solve for I4 over 4. So it's going to be 1 plus 8% over 2 to the power of 2. All of this to the power of 1 over 4, because we're taking out this, minus 1. Okay. And that is going to get you roughly 1.98%, which I'm going to store in my calculator as A for accuracy. Cool. So now we've got the correct interest rates for this period in quarterly. So now we want monthly interest rates, but we have to split it up because there's 2 different sections. So I'll do from time 10 to time 12 first. So time 10 to time 12. We want monthly, so I'm going to say 1 plus I 12 over 12 to the power of 12. And we have half yearly is equal to 1 plus I2 over 2 to the power of 2. Let's sub in what we know and solve. I12 over 12 equals 1 plus 8% over 2 to the power of 2 to the power of 1 over 12 minus 1. When we sub that into our calculator, we get 0.66%, and I'm going to save that as B. Cool. So now we've converted this interest rate to monthly. Now we just need to do this interest rate to monthly, and it's effective. Okay, so time 12 to time 15, we have 1 plus I12 over 12 to the power of 12 equals 1 plus I. We just have, we have effective. So it's just 1 plus I. Okay, let's solve for the effective monthly interest rate, which is that. That's going to be equal to 1 plus 8% to the power of 1 over 12 minus 1, which simplifies to 0.64%. And I'm going to store that in my calculator as C. Okay, So now all our interest rates are matching the correct period. So now all we need to do is make everything present valued. So this is going to be quite a long equation probably. Okay. So, and we also need to remember our x. So let's break it up into these intervals again from time 0 to 4. So we're getting x, but we're getting it half yearly. So each half year we're getting x over 2. So let's start with that. X over 2. And then we're going to have an annuity. And it's a half yearly annuity, but it's 4 years. So that means there's 8 half years in 4 years. So it's going to be times by an annuity, present value annuity for 8 years. And it's going to be at that interest rate, which we worked out for time 0 to 4, which was 4.04%. 4.04%. Cool. Now let's do our second, so these are kind of like your critical points. So these are like where you break up everything. So now we're going to do from time 4 to 5. So again, it's going to be x over 2. So let's start with that. So plus x over 2 times an annuity. And it's only 1 year, so that means we'll have 2 half-year periods. So in our annuity, we'll have 2 periods. And it's going to be at our interest rate from time 4 to 5, which we worked out was 4%. 4%, okay? But we've got to be careful here. So this present values it to time 4, right? But now we still need to present value it another 4 years. So now we're going to times that, present value that by V at an interest rate of 4.04, because that's our interest rate for those 4 years. But it's going to be for 8, because it's the power of 8, because this is in terms of half years. I hope that all makes sense. Quite a lot going on there. Okay. So now we've present valued everything in this. So now we need to present value this section. So we're getting 2x per year, but it's in quarters. So if you take 2x and you divide it by 4, it'll give you x over 2. Okay. So we say plus x over 2. So that is how much we're getting per quarter. And then we have to multiply that by an annuity, same as before. And now we have to work out how many quarters are in this period. So from time 5 to 10, it's 5 years. 5 times 4 is 20. So there's 20 quarters. 20 quarters at the interest rate, which we worked out for time 5 to time 10, which was A. So at the interest rate of A, cool. And now we need to present value that. So we basically need to, because that present values it to here, now we need to jump it back here, and then we need to jump it back here. So this is going to be at the 4% rate, and this will be at the 4.04% rate. So it's going to be V at the 4% rate for 2 half years times V at the 4.04% rate for 8 half years. Cool. That's the next one. Okay, so now let's do, so that's basically present valued everything from here. So now we just need to do these 2 periods. So this is monthly, and we're getting 4x per year. So monthly, we're going to get like 4x over 12, which will be x over 3. So it'll be plus x over 3 times an annuity. How many months are in 2 years? It's going to be 24. 24 at the interest rate, which we worked out here, which was B. Cool. And now we need to jump it back. So, because that present value is to here, so we need to jump it back there, there, there. So we need to do 20 quarters, 2 half years, 4 half years. Okay, so it's going to be times V at A, because A was our quarterly rate, to the power of 20, times V at our 4% rate, to the power of 2, so that jumps it back that year, times V at 4.04% to the power of 8. Cool. And now for our final one, this period. So again, we have 4x per month, so that means we get x over 3 per year times an annuity. It is 3 years, so that means there's 36 months in that period. So 36 at the interest rate, which we worked out for time 12 to 15, which was C. Okay, so now we've dealt with all the payments, but we've present valued it to here. Now we need to do 1, 2, 3, 4 jumps. So we need to do 24-month jump, 20 quarter jump, 2 half-year jump, 4 half-year jump. Okay. So we need to times that by V at the interest rate of B to the power of 24 months times V at an interest rate of A for 20 months, 20 quarters, times V at 4% for 2.5 years, times V at 4.04% for 8. Yeah, okay. So now I'm not going to write out the formula because it's going to take forever, but I'll just sub this into my calculator. And I get x over 2, I'll write it out to, let's say, 5 decimal places, times 6.72164 plus, so basically that's what that simplifies to. Now I'm going to work out this, so x over 2 times 1.37392 plus x over 2 times 11.03338 plus x over 3 times 10.07318 plus x over 3 times 12.46239. Cool. And now I'm just going to factor out the x, and I'll collect everything. So it's going to be x times 17.07633. And from the beginning of the question, they told us that the present value of the annuity is 2049. So 2049 is the present value, and this is all working out the present value. So we can equate this to 2049. Okay. And now if we divide both sides by this 17 point whatever, we can get x on its own, and we get x equal to 119.99. And that's the final answer. Okay, let's have a look at question 5. Question 5 says evaluate the present value of the following payment stream. Assume that time is in years and that the annual effective interest rate is 10%. Okay, so let's have a look what we've got. So it seems like it follows a pattern. So at time 1, we pay 100, 200, 300, and then it goes back to 100, 200, 300. And it seems like this pattern continues until time 99. Okay, so often when you have these varying payment streams, you want to kind of treat it as 3 different ones. So you can treat these hundreds as an annuity, you can treat these 200s as an annuity, and you can treat these 300s as an annuity. And to find the present value, we're just going to add them all up. Okay, but we see that they're all 3 years apart, right? Like time 1, time 4, the next one will be at time 7, time 10. So instead of we're given the annual effective interest rate, we want the 3-year effective interest rate. Because the 3-year effective interest rate will be easier to work with when you're doing this annuity. Okay, so we want 1 plus I to the 1 over 3. Because remember, like, if it's compounded 3 times a year, then it would be, it's not to the power of, it's just like in brackets 3. But since it's compounded every 3 years, it's like 1 over 3. That's just how you do it. Divided by 1 over 3 to the power of 1 over 3. And that's going to be equal to 1 plus I, because that's what we're given. And I is 10%. So now we're trying to solve for this part, because that would give us the effective 3-year rate. So I 1 over 3 over 1 over 3 is equal to 1 plus I. I'm going to raise both sides to 3 to get rid of this. So sorry, and I is, what is I? 10%. Yeah. So let me just 1 plus 10% to the power of 3 minus 1. Cool. And when I sub that into my calculator, I get 33.1%. Okay, so that's our, let's write out what this is. This is our 3-year effective rate. Cool. So now the present value should actually be quite easy, right? So the present value is going to be equal to, so let's do the 100 first. 100 times an annuity. And we should note that it's in advance, because we can't really do it in arrears, because you'd have to go back like 3 periods. You have to be at time like -2. It doesn't make sense. So we're going to do all these annuities in advance. So 100 in advance. And let's think about how many periods it has, right? So there's 3 payments, and it's made till time 99. So that means each one will have 33 like occurrences. Okay, so 33 at the interest rate which is worked out, which was 33.1%. And then that will, because since we're doing it in advance, it's going to present value to here. But now we still need to move it back 1 period, because we want it at time 0. So we're going to have to do times v to the power of 1, and we'll just use the 1-year effective, which is 10%. Cool. Now let's do the 200. So it's going to be very similar. 200 times an annuity in advance, and there's going to be 33 payments at 33.1%. The only difference is that now we have present value limited time here, but we want to do 2 more years back, so we're going to times it by v to the power of 2 at 10%. Okay, and finally 300 in advance, 33 at 33.1%. And we'll have to move it back 3 years. So this one you could do in arrears, but it's just going to make the calculations harder. So I'd rather just do it like this. Okay, good stuff. So now we see we have this common factor. So I'm just going to work out what it is once, and then we can just sub it in a bunch of times. So present value annuity for 33 periods at 33.1% is going to be 1 minus 1.331 to the power of negative 33 over 33.1%. And if we sub that into a calculator, it gives us 4.02, which I will store as A. Okay, so now to find the present value, all we need to do is sub it in. So it'll be 100 times A times 1.1 to the negative 1 plus 200A times 1.1 to the negative 2 plus 300 times A times 1.1 to the negative 3. And finally, when we sub that into our calculator, we get 1,936.4. Cool. I hope you enjoyed this video. Some of the questions were quite tricky, so I hope you followed along there, and I'll see you in the next one.